Welcome everyone to the Mining Mentoring Program. It is an initiative organized between the NGO TAG NG from Nigeria and the NG. I'm hearing yes, and the NGE. It's a geology students organization from Nova University from Lisbon. Okay, a little bit about the NGO, the organization. We are NGO focused on SDG 4, education accessible for all, and we want to provide quality education and opportunities through our trainings, seminars, and other initiatives. We also want to lead by example and build the great leaders who can affect positive changes in their immediate communities, especially in Africa and other countries that are considering under development, but that it's a harsh place of opportunities, especially through these initiatives. We also love to be part of the success stories of our students and our followers. And for this, we will continue to be a source of motivation and joy to people willing to take positive actions in their generation. A little bit about the NGE. They are a geology students organization from Nova, as I told you before, and they have more than 20 years of activity. Their role in the university is receiving new students, organizing field trips, company shows, events, and support the daily initiatives of the Earth Science Department, professors, and also the other students that are not part of the organization. Now, about our speaker, Dr. Korting. So you hold a PhD in geoscience from the Potsdam University, right? And your dissertation name was Hybrid Imaging Spectroscopy Approaches for Open Pit Mining Environments. Now you are working as a geological hyperspectral application specialist at ISPEC. And today we have the pleasure to hear you talking about application of drones and ground-based hyperspectral imaging for mining applications. So I will allow you now to talk and share with us everything that you want to say. Thank you.
Great. Let me just share my screen, and then I'm probably not going to go into full screen mode because otherwise I will not be able to see the chat. Okay, I'm already not able to see the chat. So if some questions come up, please let me know that you guys can monitor a little bit. So the proposed title for today is that I'm going to talk about applications of drone and ground-based hyperspectral in the mineral and mining industry and raw materials industry. I would prefer for this to be more of a not discussion, but at least getting some feedback and input from you guys. So don't be shy if you have some questions or comments. I'm going to ask specifically after specific blocks of topics are being finished. The first thing, and I just put that on a slide now because I tend to forget, I'm working with HySpecs, which is a company developing hyperspectral cameras in Norway. And we're doing a lot of R&D, and we're also supporting students. So if you have a student project in mind, if you want to do an internship, if you have anything where you want to have some training with us, please don't hesitate to reach out. Just find me on LinkedIn and text, and we can figure something out because we love to support students, and we are very happy to spend time on that. So don't feel like you're imposing on that. So that's the first point. So I will not forget saying it in the end in case we have to rush a little bit. So I figured that a lot of people might not have a lot of background on spectroscopy in general and then hyperspectral imaging specifically. So we're going into a little excursion for that, just to give you some of the technology background. Also wanted to highlight a couple of things about the current challenges. But first of all, let me know if you can see the slides okay here, because I'm not going to make them bigger so we don't lose context too much. Cool. Do you see your own videos on the side here? Are they overlapping, or can you see the full thing? It's overlapping. I can't hear very well, Andre. Can you repeat?
Sorry. We can see the videos on left, but the slide is a little bit cut on the right, in mirror, you know.
Yeah.
On your right.
On my right, then I will just make this smaller so I can see you guys as well.
Yeah.
Here we go.
It's okay. It's okay.
That's perfect. So just as an intro that you might be more familiar with than with hyperspectral is, why are we looking for new technologies and why are we still trying to bring innovation into mining? What kind of challenges is mining expecting? And I think there's or experiencing at the moment, there's a lot of things coming together that influence each other negatively in some parts. So this is just a reminder that we're all aware that there's declining head grades, we have deeper deposits, it's harder to not only find, but also to extract the amount of material that we need in order to bring technology forward. We have a higher metal demand due to the green shift, and that means more specialized minerals and materials and metals that are needed, not only more, but also more specialized. So this is a stronger diversification of the resources where we see a very high variability in minerals that are needed for high tech, and not only a high variability, but also a very changing variability. So we have a very high turnover rate of technology at the moment where a lot of innovation is taking place, which is great. But that also means that we change frequently which metals are needed, and mining projects are not that proactive. It's very hard to follow trends with a mining project. We have to be a bit more proactive. On top of that, we're experiencing different geopolitical risks and supply chain disruptions. That's not only shown by COVID, but also by the current conflict in Ukraine. We have different expectations for sustainable practices and responsibility. And today is a good example for that. We have very diversified stakeholders, not only in the learning experience and sharing of information, but also a diversified pool of stakeholders that can influence decisions in mining. So public opinion matters more than it did 20 years or 50 years ago. And all of that comes together in shaping how innovation is perceived in the mining industry and what kind of market we're also servicing, right? So that's a very broad intro to mining and why innovation is needed, but also why innovation is keeping this very flexible and volatile. Then for spectroscopy, just in case you have never heard of spectroscopy or you haven't really used any kind of spectrometer before. So with spectroscopy, we study the light as a function of the wavelengths or of its wavelengths. So we have incoming energy onto a surface and we are collecting the outgoing energy from that surface, and that is influenced by chemical bonds in the material and by the crystalline structure in terms of mineral structure and crystalline materials, but also in amorphous materials. And when you look at the example here, simplified, we can see that all of these 6 different minerals, they show different spectral expressions in the wavelengths region that we look at, which is around 400 to 2,500 nanometers. And we can identify a material by the position and shape of an absorption feature. So this is an absorption feature down here. And we are talking in reflectance most usually. And the depth of this absorption feature can give us a semi-quantification. So the deeper the feature, the more of this material is expected, or the more spectrally pure that material is. Just as a very brief intro to that. What we're also doing with most of these systems and most of the systems on the market, this is a push-broom architecture. And this is very easy to understand when you think about satellites, where we have a camera moving over the Earth's surface and is collecting an image by collecting a line of pixels and then collecting the next line whenever that satellite is in the next position geographically. So we're going over the image, collecting as we go. This is called push-broom architecture. And the HySpeX cameras that we're using, they work as a push-broom architecture as well, which means we have a line of pixels that we're collecting. And then either the camera moves over the sample for example, as a UAV camera system that flies over an area, or we have a lab setup where the samples move under the camera, for example, a conveyor belt where the sample is moving instead of the camera. And that way we're collecting a hyperspectral image where each pixel represents a spectral dimension or a third spectral dimension. So we are usually talking about hyperspectral image cubes. In the XY dimension, we have our image dimension and our spatial resolution and dimension. And in the Z dimension, we usually have the lambda, so the spectral dimension, which is each wavelength. And that's why we say or talk about it as cube, because we have up to 500 spectral bands that we're collecting. Something about the wavelength ranges, we're usually talking in abbreviations here, so I just want to make sure that some of these are quite self-explanatory. So we have different wavelength ranges in which remote sensing is being usually remote sensing or remote sensing data is being collected. For hyperspectral imaging, we usually talk about the visible to near infrared, which is around 400 to 1000 nanometers, and then the shortwave infrared called SPHERE, which is from 1000 to 2500 or 3000 nanometers, depending on the definition that you're looking after. And then we have the long wave infrared, which is after 3000 nanometers. So usually around 5 micron and onward. And today we're only talking about the Vinian sphere, so 400 to 1000 nanometers, and then 1000 to 2500 nanometers. And in this wavelength range, we have different effects in the material that cause the absorption features that we're looking at. So when we look at a spectral plot here, we have the visible to near infrared up to 1000, and then the sphere. We can see that in the Vinier, we usually see very broad absorption features, most likely more broad absorption features that are wide and quite deep. And those are caused by transition element bearing oxides and hydroxides. And we also see rare earth elements, usually neodymium, quite well. So these are the features that we're expecting to see in the Vinier, and that could mean that we're seeing secondary iron quite well, or we see gossans over deposits in that wavelength region. And then in the shortwave infrared, we see hydroxyl-bearing silicates, either dioctahedral or trioctahedral. So that means we're seeing different kind of clay minerals quite well. We can see micas quite well, in different kinds of micas and white mica. And we also see something like chlorite, tremolite, actinolite, and then carbonate, and also sulfates. This is more interesting and will depend a little bit more on which deposit you're looking at and what minerals you're interested in, and what minerals can be used as proxies to vector towards mineralization or showcase contamination, or whatever the actual purpose of the data that is being acquired is. Another distinction that we need to make is, I've talked about hyperspectral already, but I want to give you an idea of what the difference is between multi, super, and hyperspectral. So a lot of the data sets that geologists would usually see in mine are multispectral data sets that are collected by freely available sensors. And here we're talking Sentinel-2 or Landsat, or having archive data from ASTAR, which is a satellite that is not actively acquiring anymore. But there's a lot of archive data that is often used for exploration purposes. And for multispectral data, we usually have a limited number of bands, up to 15 at most. So we have wavelength regions that are being collected in very wide bands, so we don't get a lot of information, which means we have maybe 8 or 9 different data points in the Vinier and then 3 in the sphere. And you can see down here in green, this is what a spectrum would look like. And all of these spectra here are from the same material. So we can see that there is a change, or we can see this iron feature that I talked about before a little bit in Sentinel-2. And then just because we don't have a lot of information in the sphere, we just get a general slope, basically, for Sentinel-2 in that case. Then we have commercial satellite data, and some of those are superspectral, so they collect more bands and more detail spectrally, but also spatially. An example here for that one is Worldview 3, which you can call superspectral. It's not, it's more of a soft definition for superspectral, but you can see that it has considerably more number of bands, and it covers a little bit more detail in the spectral range. And we are able to resolve some of the features in the sphere here, but we're also able to resolve changes in the slope in the Vinier here, which is also indicative for iron in that case. And then hyperspectral hyperspectral cameras collect the incoming light in in a large number of overlapping consecutive bands. That way we are able to resolve very, very fine features. So you can see that we're able to collect information about a double feature down here, or we're able to model the slope here a little bit better. And of course, hyperspectral, and the one that I'm just showing schematically here, hyperspectral can be 100 bands up to 500 bands or even more. They will also be affected by atmosphere. So one of the main reasons why we see these huge gaps in the multispectral is because the atmosphere from when a satellite takes an image, the atmosphere is just affecting what kind of signal we get back from the Earth's surface into the sensor, into the detector. So hyperspectral technically would also have these gaps here, and we can see that a little bit in the UAV data later. And that just has to do with the aerosols in the atmosphere and oxygen affecting it, and then water vapor affecting it quite a bit. So hyperspectral is not a solution for that. It will just give you a higher resolution in the bands that are not masked by the atmosphere. Just another distinction here is there are hyperspectral satellites as well. We have different platforms where we can use hyperspectral. Today I'm talking a little bit more about UAS or UAV, and then the tripod, so ground-based scanning. And you can see the ground-based scanning just as a schema here. But there's different ways to look at data acquisition and why we would be interested to do that in the lab or in the field or from a UAV or a satellite. And a lot of that has to do with the spatial resolution. So how big are our pixels and how much change do we need to detect spatially? And also the temporal revisit time, basically. So how often do we need to scan something? If it's an exploration project and we just want to find really big features and make sure that we do a drilling campaign, UAV or satellite could be viable. If we need to find small areas in an outcrop or in an open mine in order to extract material more in more detail, not knowing the right English word, but like if we want to have a more determined extraction, then we might need a centimeter resolution, or at least a resolution that enables or is similar to our shovel size, so that we can extract material instead of having 30-meter pixels, for example. So all of these are considerations and why we would be using UAV or satellite or tripod, and it's often a case-to-case study. I'm just going to give you some example cases. Then I already said not all materials or all minerals are spectrally active in the Vimy and SWIR spectral range, in the wavelengths range. I just made a very, this is a short list and condensed from Krupnik et al. From 2019. So if you're interested, I would advise you to just look at that paper, where they're doing a really good overview of how and where hyperspectral has been used in the mineral industry as the status of 2019. But generally, we can see that carbonates, hydroxides, sulfates, they give us strong features in the shortwave infrared and some in the visible to near infrared. Oxides like iron oxides, chromite, and also rare earth oxides are very viable. And then we see different silicates, not all of them, but different silicates that would be consistent with alteration patterns that we seek on the surface. And this is something where hyperspectral has been used a lot to find specific alteration patterns on the surface for exploration or for updating geological maps, for example. And a prime example here is that micas, chlorides, clay minerals, especially different types of clay minerals, even though they're amorphous, they can be detected very well with spectroscopy. Okay, so I'm going to leave that for the end if we still have time. I just wanted to give you an overview where this can be used, but we're concentrating on the run of mine, run of dump, or even exploration, which isn't really part of this flow sheet. But these cameras, if you can do a quality control with a camera, you can basically put that wherever in the process you need a quality control or detection of contamination. So I'm usually trying to put this into 4 different categories. We use the cameras for exploration, just to scan larger areas. If we're talking UAV, we have a pixel size of 10 centimeters, plus minus some, depending on the terrain. This can give you a really good idea about patterns that are emerging that are not visible in our visible range. That's why we're trying to extend it. We're trying to help with targeted drilling campaigns or sampling campaigns, or just pointing out areas of interest in a larger concession, just to make sure that you're spending less time on the ground with the people that are needed to do the field work. This is also true for very inaccessible terrain, where you can just scan without having to put people in danger. Then we have a close-to-face sorting aspect, or selective mining. So this is what I said before. You can monitor grade, or you can monitor contamination, or even, for example, clay content in a mine phase, to make sure that you're extracting at the right area, or extracting in an area where you expect to have a higher control afterward for grade control, or even reject waste instead of putting it into the processing. Conveyor belt monitoring, same thing. Once we have a model and we know what minerals we're looking for, if you need to know if you have too much talc in the process, or after a SAG mill, you can put it over a conveyor belt, and then you'll get more proactive approach in adjusting the processing afterwards, or even discarding material. So that also has a sorting aspect. And then one method where it's used a lot is drill core scanning. And there's a lot of different companies that do drill core scanning using hyperspectral, and that is usually showing patterns in the drill core and in the data, mapping mineral occurrences, and helping with the deposit modeling and consistent tracking. Instead of having geologists track, the geologists will do a data analysis, and then we have a consistent digital archive for the drill core. So today we are looking at UAV data acquisition. This is our current system that we're using. So we have a hyperspectral camera that can be mounted on a UAV. And then what we call ground-based is usually a tripod field data acquisition, where the same camera can be mounted on a tripod and we can scan an outcrop. And before I go into the first application case, are there any questions up to here? I see that the chat has something to offer, but I'm not able to see it just now.
Yeah, about the chat, it's people are asking for the others make questions. So until now, we don't have any question. But Anthony is saying that in Nigeria, this is using for mapping.
Yeah, it's because this is not a program. This is what HySpecs is doing, is offering the technology in the camera. I'm not aware of anyone using it from us, or a system being sold to Nigeria. There are service providers that use the cameras. So there might be, people use.
Probably the methodology, not your equipment in specific,
Yeah, and I mean, ASTA is, even though it's not published, ASTA data is used a lot for exploration, or even just for, I forgot what that is called, but if you need to give a report to investors, ASTA data is one of the data sets that is still available for free on the USGS archive, and often used to just showcase potential for large areas. But for ASTA, we're talking 30 by 30 meter pixels.
Yeah, I saw you were talking about the features, the identification of the features, and I had my PhD was in this area, and we talked before about it, and I had many challenges in the shortwave to find about features about lithium, for example.
Yeah.
For copper, zinc, and arsenic, I found some interesting information. About lithium was not easy at all.
No, and there's some areas where it might work for the lithology. So you have spectra that can determine different lithologies, but not elements. And sometimes the minerals themselves are maybe they can be distinguished in the lab, but then you can't distinguish them in satellite data or in airborne data, because the atmosphere is just masking everything that was interesting to you before. So even if it's feasible in the lab, you still have to explore how distinguishable it is in real life data, basically. Yeah. So it's very much a case by case if it's possible to detect the deposit that you're interested in.
Yes, and it's highly sensitive too. It varies a lot about the mineral organization, structure, and also the coexistence of other minerals. I feel it a lot, and we try not only the depth of the feature, but also the area, the open of the feature, and a lot of variables. And it was not easy to find this specific mineral.
Yeah, agreed. For some, it's very doable, and for some, you just have to accept that that's not the method that will get you forward. There's always that payoff. Yeah, true. Yeah. Okay. Is there more questions?
Yeah, we have a question in the chat. Is the iSpec works also in faults with short thickness, so we can't see in the mineralization query?
I don't think I understand the question perfectly. You mean because HiSpecs is just a surface measure, so we are always only seeing penetration depth as half the wavelengths as a rule of thumb. So penetration depth at best is 1,000 nanometers.
Okay.
So it's only a surface measure. That's why it's also affected by weathering, state of weathering. Yeah.
Can you see the chat so
yes,
you can follow the questions now? It's better.
Yeah. What do you mean by program? Because if we do, the question is, do we have access to the program? I want to be trained on how to use it. So I think there's a lot of different resources online as an intro to using hyperspectral and to understand hyperspectral data. I'd be happy to just find some for you and then share them. Maybe Andre, you can share them with everyone who signed up for this and just share it via email. Yeah.
Yes, we can. But I think Abraham is thinking that iSpec it's a software maybe, but no, it's a company that works with this kind of applications in the geoscience, right?
Yeah. So HiSpecs is a camera developer. So what HiSpecs is doing is developing cameras that give you high quality hyperspectral data in the linear and sphere wavelength ranges. And we do applications as well. So we're able to analyze with clients and with universities and for master's projects and any kind of student project as well to go into the feasibility of specific applications. So we have a really high R&D aspect, but the core business of HiSpecs is to sell the cameras to be used. And we are working together with a software company called Predictera. They're based in Sweden. I have some slides on that later. They are doing a software where you can have a month of trial with trial data if you want to have a look at data specifically. We can also share that link with you. So then you have a better idea of what this data looks like specifically. Yeah.
You have another question. What type of iSpectral data is suited to map carbonate bodies and rare earth elements?
Great question, because both of them are very doable. So it's always an easy solve. So for carbonatites, for carbonates, we usually use the shortwave infrared. Specifically, there's you can differentiate between different types of carbonates. There's a shift in the spectra around 2320 and 2340 nanometers, so the end of the shortwave infrared spectrum. For rare earth elements, we usually use the linear. There's 3 very specific and narrow absorption features for neodymium that can be detected, and the presence of these features is a very good vector for other rare earths, because neodymium is usually present in the mineralization, even if we're looking for other rare earth elements. And I think, I'm not sure, I don't want to lie, but I think the rare earth element, there's papers publishing that's visible starting at 300 ppm of neodymium. So that feature is quite dominant. But then, of course, we need to figure out if you have a 1 by 1 meter pixel, how much neodymium is in there to actually show in the matrix of a rock.
Yeah.
But yeah, so that's definitely doable. And then I'm going to take Abraham's question as well and just continue with one of the case studies. So for the applications that can be used with our camera, I have, just if we go in that schematic, I think that might help just to understand where we would place cameras and which applications. So we have drone-based applications, and in mining that could mean tailings monitoring, it could mean the monitoring of mine faces and exploration. I would say that's the 3 main applications where UAV-based scanning is being used, at least in primary materials. So I'm not talking about any secondary or recycling opportunities at that point. And stockpile management, so everything in mine where you want to scan a bigger area. For UAV, we're talking pixel size of around 10 centimeters, 6 to 10 centimeters. If we're mounting a camera on top of a conveyor, you could mount a camera on top of a truck loading station or truck weighing station, but you can also mount it on top of every conveyor, basically, depending on what you're interested in. The only limitation here is water content of the material. So ideally, we wouldn't put it, or we haven't tried it, for example, over flotation cells or something like that. Ideally, the material is not in water suspension. And that goes for grade control as well. We're using it for core scanning quite a bit, and that's one of the main applications, or one of the standard applications of hyperspectral in mining at the moment. We have people using it to scan leaching heaps, to see the process of leaching and the progress, basically. So there's a lot of different applications. If you need to distinguish a pattern on the surface that is indicative for what's underneath, on a general term, you can use hyperspectral. Okay, cool. Let me just continue, but yes, we can share the presentation with you afterwards. We'll just do that via mail. And I think the presentation itself is being recorded, so you should have access to everything. Okay, awesome. Thank you for your questions. I appreciate that. Okay, first example is an exploration project. And this is a copper volcanogenic massive sulfide alteration pattern. I'm saying that it's an alteration pattern because there's no actual open mining. There's not enough copper in there to open a mine, but the alteration patterns are the same as in an area where we would want to start a project. And this is in Cooperite, Nevada. And we're using this example because it's one of the standard areas where hyperspectral and multispectral sensors are being tested. This has been the playground of the USGS for many, many years when the whole application started and the whole technology was developed. So there's a lot of papers on Cooperite, Nevada. If you look for that in Google Scholar, you will find a lot of examples from when this technology started and who developed it, and still today, where this is being used. And this area is very well explored and defined. So HySpecs had a UAV mineral mapping campaign in Cooperite because this is a alteration of advanced argillic alteration. And we have very well exposed zones on both sides of, in the middle here is Highway 95 in Nevada. We have different alteration patterns in the west and in the east, and we concentrated on the western part of that alteration zone. So we have just a small subset area that has been flown here over that area. And this is the UAV data. Just in comparison, this is the Sentinel-2 data over the same area, just to give you an idea about spatial resolution as well. And the flight campaign here, we covered 40 hectares of the western center of the Cooperite Hills in 20 different flight lines within 2 days. The altitude of the flight is usually around 120 meters, depending on the topography that we are scanning. And at that, in that altitude of flight, we have around 10 centimeters of pixel size. Just to give you an idea of what our system looks like, I don't have a video at that point, but this is the system that we are using to fly. We have our HySpecs camera here mounted to the UAV. and then a heavy-duty UAV octocopter. And the high-spec system that we're usually using is it's called Mjolnir, and we're using a VS, which means it's the visible to near infrared and shortwave infrared. So we're covering the full wavelength range. But high-specs is also offering these separately. For example, if you're interested in carbonatites, you wouldn't need to buy the whole system. If you're interested in rare earth, maybe you don't need the shortwave infrared. And additionally to the hyperspectral data that is acquired, you can mount a LiDAR, so you can get a DSM while you fly. So we have a LiDAR to get an accurate point cloud. Yeah, so that's basically the system that we're using. I don't want to go too much into the technicalities here. The only thing that I want to show you from that slide is just to remind you of the wavelength range, 400 to 2,500 nanometers in total. And the whole system here is around 6 kilo payload for the drone, which means the drone is below 25 kilos, but just, which keeps it in a specific drone category that can still be flown more easily in most countries. But yeah, so we're around 6 kilo payload for that drone. Yeah, and we're using a new drone at the moment, which is from Black Square, which is a Colombian drone developer. So we have a very specialized system for the camera, and this is how we use it on a day-to-day basis. Just to give you an idea about the actual, so this is the full data set. We're using a subset in the next couple of slides, but this is the full data set. You can see how the different flight lines are being mosaicked together. It's usually the case that these have around 25% overlap, so that we're not getting an incomplete mosaic of an area. But you can see we have a little bit of an overlap miss in that black area here, for example. And then you usually get raw data or radiometrically calibrated data that is corrected to reflectance. And I just wanted to show you what a UAV reflectance spectrum looks like, because it's different from the perfect lab spectra that we usually see. So you can see we have these interpolated strips here. Like, I'm not sure if you can see the mouse. I hope you can. We have an interpolation here, and that's basically because the atmosphere is affecting our data there quite a bit. And that's where we don't have an atmospheric window, is what it's called. So we have to exclude that data. What we can also see is that we get a really good impression of the actual iron feature that we usually see in the veneer. And then starting at around 2,100 nanometers, we get the mineral features that we're used to from the laboratory. Okay, cuprite. Just the general geological map at a high level overview. We were at the western center of cuprite, specifically somewhere in this area. So what we're expecting is alunite alterations, hydrated silica, some are advanced argillic, but also some argillic alteration, like white mica, montmorillonite, kaolinite. Generally, you can see 3 spectra here. We have the alunite in red, we have the kaolinite and the buddingtonite in that case. You can see where those look similar and also where they differ quite a bit. But also we can see that some of those features, specifically alunite, where we see this nice double feature here, this will be masked by the atmosphere, as we saw before. Like, this is an area where we don't get information just because the atmosphere, even if we're not scanning with a satellite, but with 120 meters, just the water vapor in the atmosphere will affect our data. So what we're concentrating on is everything after 2,100 nanometers and then before 1,000, basically. So we lose a lot of the spectral channels, but we get a lot of resolution in those channels still. Okay, this is going a little bit more into the mineral spectral properties. It just serves the purpose of comparing. So all of these are kaolinites, alunites, sorry. All of these are alunites, but the spectra differ quite a bit because the ALH bonds in the minerals themselves and the substitution of potassium, sodium, calcium affect the actual spectrum. It goes a bit too much into depth here to go into how that is affected and how we can model that. And if we want to model it, just for you to be aware that there are minuscule changes between those. But when you look at them in general, the absorption features that we observe, even though they might differ a little bit, are still indicative of alunite in its most generic form here. Okay, I also wanted to give another comparison between the satellite versus hyperspectral, multispectral versus hyperspectral, both spatially and spectrally. One thing is that what I'm showing here is the kaolinite spectra, a very typical double feature. I highlighted it here in red, but this is what we would call a double feature. We have two minimas in the same or very close to each other within the same general absorption feature. And you can see that when we lose the spatial resolution, we lose this double feature quite quickly. So the hyperspectral cameras, the shortwave infrared cameras that we have, they have around 6 nanometers spectral sampling. So we are still able to resolve this double feature. As soon as you go into 10, 15, 20 nanometers, we only have a single feature here. So we're losing information that can help us to distinguish between different minerals. There's been a lot of research in that, but especially for kaolinite or clay minerals and white mica absorption, the exact position of the feature is very important to not only distinguish the mineral, but also to distinguish the position based on temperature, pressure of when that material was formed. So we need to keep in mind that spatial resolution and spectral resolution, is not only nice to have, but for some applications it is quite important and relevant. And just to give you an example in comparison here. So we talked about that. So what we look at here is the Sentinel-2 data compared to the hyperspectral data in the same area. Sentinel-2 has 20 meter pixels, HySpecs has 10 centimeters. I'm not saying that you always need 10 centimeters, because with 10 centimeter resolution, we also have a very big data volume that you're dealing with. But if you need to figure out specific areas that you want to look at in more detail, or if you have smaller patterns that you want to resolve, you need to realize that 20 meters might not be enough. And that's not only visually less appealing, it also means that if we have 20 by 20 meters, we get a mixture of material that we are looking at spectrally. So if you have a couple of trees and then kaolinite and montmorillonite and quartz in the same 20 by 20 meters, which is quite common, basically, we might lose information about the spectral properties of the material that we're actually looking for, because it gets mixed into with the vegetation spectra and with the quartz spectra. So for some applications, we also need to figure out how spectrally resolved we need it and how mixed we can accept pixels to be. And because it's still quite, if you have never seen spectral data or you have never seen a spectrum, it's still quite high level. So I'm trying to just give you another example of that. So basically, this would be a library that we're interested in, and all of these are spectra that we're interested in for skarn deposit. So we have hydrothermal alteration of a carbonatite. You can see that there's quite small changes in spectral information that we're interested in, that we're trying to resolve. When we look at that library in hyperspectral, you can see that we can resolve a lot of different changes, especially when we look at the 2100 to 2500 nanometers. When you look at the ASTA data, and ASTA is favorable here because we have more bands and more information in the shortwave infrared than Sentinel-2. We can see some changes of where a feature is positioned, but we're losing quite a bit of distinction between those. So just so you're aware, when we talk about ASTA data, we're not only talking about 30 by 30 meters, so it's visually less resolved. We're also talking about the spectral difference between the left plot and the right plot. And just to show that as a comparison of what we get as a result when we use a very simple mapping of each pixel. So on the right, you see the HySpecs UAV image, 10 centimeter resolution. And what is not really visually determinable in the RGB is that we have the center of, which is mapped as alunite here. We have a pattern here that we can't see otherwise. So in the 10 centimeter pixels in the hyperspectral, we see an area that seems to be interesting to go explore in more detail. If we look at the ASTA data, not only will it be hard to pinpoint the exact position of that, but we might just be interested in the larger scope. But also because we're mixing pixels and we're mixing the spectral signal, it is suddenly not classified as alunite anymore, but as kaolinite. So we are also we're losing spectral information. And it still shows up as something that seems worth exploring because it shows up as kaolinite, and maybe we expect kaolinite to be an alteration mineral in the surface. I just want to make you aware of the changes that we can expect between these two data sets. And then the last two slides on cuprite, or in this specific mosaic. Another very typical technique is to look or do a feature modeling where we look for the position of a feature, the wavelength position, and how that position changes in nanometer. So what we are doing here is called spectral feature modeling, and it can show us patterns and show us patterns in the spectral data without labeling them at first. It can give us a good idea, but the labeling is the hard part. So you also have to distinguish if you need to see patterns or want to point towards areas of interest, or if you need to label based on mineralogy. But what we can see as result here, if we look at the spectral pattern analysis, or let's say spectral feature modeling, and what we're modeling is the deepest feature at a wavelength in a wavelength range, the second deepest feature, the third deepest feature. So it's sorted by depth. And we can see here the deepest feature. When we just model one feature, it seems like this is a more or less homogeneous area. Everything is classified as clay or mica around 2,200 nanometers in green. But as soon as you go into the next feature, the spectral absorption feature, we see a clear west-east divide. And then for the third feature, we see that it's not only an east-west divide, there's also something happening in that center of what we have formerly distinguished as possibly alunitic. So it gives us a really good idea about patterns. I'm not saying that any kind of labeling here is trivial though. Okay, that would bring me to the next example. So if there are any questions in the chat, let me just check. I'm not sure if I have.
No, until now, there's no one question now.
From Anthony, if the app can be used for regional underground water survey, no, because we can only see the surface. Sometimes it depends on how loose the material is. So for example, for stockpiles or even tailings, the surface water expression might be indicative for the general water saturation, but no, not for water surveys as such.
Yeah. I think for water applications you have radar, but it's only 15 or 20 centimeters. It's just for water content, not even for underground water applications.
I'm not an expert in radar, but I think you can go deeper, but I think the spatial resolution is quite coarse.
Yeah, exactly. You lose in resolution, you gain in depth.
Yeah, exactly. Yeah. Okay, then let me carry on. I need a drinking break soon, but let's do another.
No, but if you need to make a short break, it's okay.
No, let's go until 6 and then
a
very quick break so no one falls asleep, and then we'll collect some questions and continue.
Okay.
Okay, cool. The next application or the next example is a copper skarn deposit. It's in Arizona called Burro Pit. So this was a project with Excelsior Mining and Darling Ltd, which is a service provider that works with our cameras. Burro Pit itself is a copper skarn deposit. It's one of two pits that are being developed or are developed. It's in the Mexican highland region of the Basin and Range province. And what we're looking at is what we did here is look at general pattern detection and potential surface expressions that we can map that can tell us something about the location of pyrite, even though pyrite itself is not spectrally active. Just to give you an idea about the area that we scanned. So this was a demo that we did in January 2022, which was a live demo on site. So we scanned a limited area of that open pit. And what you can see here is just the overlay of the data on the Google 3D model, or the DSM in that case. And you can already see in that DSM that we see a distinction between an area down towards the Pitt Lake and then towards the top flank. And in geological terms, let me just double check here. So this was communicated to me from the Chief Geological Officer at Excelsior Mining. So I can just repeat what she told me. But in general, we have a couple of faults going through here. So in red, we have the fault lines. And then they're expecting 4 different lithologies. So they have something called Upper Abrigo, which is a dolomitic beds with quartzite and calcsilicate minerals. They have granulated limestone with shale. And then they have diopside. And then the part down here is secondary. So that is basically not a tailing, but is mine waste that has been deposited here. And what we're interested in that area is getting an idea about pyrite presence or occurrence, and also just a general idea of the main minerals that we can expect from that kind of deposit. And that is, in that case, this spectral library that I showed you before, at least the different materials plotted against each other. What we're looking here at is different carbonates. So we have calcite, dolomite, iron carbonate as well, like siderite. And then we have typical secondary copper minerals. And we're also interested in the secondary iron. And why are we interested in secondary iron? Because usually if pyrite weathers on the surface or comes in contact and oxidizes, we would expect some of the secondary iron. And that's often used as an indicator for presence of reactive sulfides. If we see jarosite, hematite, goethite at different stages, it's just an indicator for different stages of oxidation, basically. And again, so this is the mosaic here. Just wanted to show you the actual data that we're looking at. You can see that what I highlighted in red here, again, the atmospheric bands are not useful to us. What we're looking at is the veneer and the large feature that you can see here, which is an indicator for iron and often used to map secondary iron. And then we're looking at this wavelength range here. So this is the kind of data that we're working with and that our analysis is based on. And here I just wanted to dive into some of the interpretation of the analysis. So what we did here is use the library that I showed you before, technique called spectral angle mapper, which is at its core just a correlator between a known spectrum and an unknown pixel spectrum. And you can see that in this area down here in orange, it maps the presence of jarosite. And that's usually used as the most reactive weathering or first weathering product of pyrite at the surface, depending on how much time it has and how reactive it is. But the presence of jarosite here is an indicator for pyrite or chalcopyrite, and thereby an indicator for mineralization, which makes sense when we're looking at the open pit that we would extract material on that flank if we expect pyrite to be there. So it's a validation of what has been done so far. What we also see is that we have a bit of a divide between areas that are more clay-rich versus areas that are more calcsilicate-rich. So we know that the mining development will most likely go into this area instead of going into an area where we see hematite and goethite cropping up. Another example for how to use this kind of data and was often used at the moment and also explored for tailings monitoring and AMD monitoring, so more environmental parameter monitoring, is using secondary iron as a proxy for leachability or reactivity of the surface. And that's just wanted to highlight that here. It's the same map that we saw before. Just in this case, we know that hematite represents a more neutral pH, so lower leachability. Goethite is an intermediate product between that, still having some reactive potential. And then jarosite, in this case, indicates a low pH with a higher acidity. So for tailings, or if we were monitoring tailings, that could give us an indicator about the stability of the tailing, the presence of water in a tailing or in a waste landscape. And it could also tell us about monitoring, identifying areas that need to be monitored in more detail, especially when we talk about acid mine drainage. And then I'm just going to skip over that. We did the same analysis here for the absorption features than we did for Cuprite. So this is going to give us patterns without us being able to label those patterns necessarily. It's a bit clearer here because we are working with carbonates. So I wanted to show you the features that we expect from carbonates. Those are around 2,340 nanometers or 2,320, depending on if we're looking at calcite or dolomite. The green spectrum here in that plot is a handbook dolomite feature. So that's a very nice feature that we would expect. And what we're modeling is the depth of this feature and the wavelength position. And I can just show you the result here. So again, the wavelength position is the color coding. So depending on what color, we can say the wavelength or the dominant feature here is around 2,200 nanometers because it's green or color coded in green. And then the depth of the feature or strength is the brightness. So the brighter a pixel is, the more clear that feature appears. And we can see that we are expecting quite clear features around 2,200 as well as 2,320 or 40 nanometers. And that's exactly what we can see here. And using that technology, we are not necessarily looking at the jarosite or looking at reactivity, but we see this very clear divide between what has been deposited as a secondary mixture or as mine waste, where we see a lot of weathering potential by possibly having non-in situ material, could be clay as well, and by having the in situ material here in bluer colors. Yeah. Okay. Any more questions in the chat? No? I'm gonna just take a minute to drink. Maybe more questions are coming up. Yeah.
You have a question?
Yeah, there's a GNSS INS solution in the sensor. I purposely did not go into that because I'm not a hardware person, but you can find all of that on our website. So there's an inertial navigation system, and yeah, we have I think the accuracy of the solution is plus minus 5 centimeters, something like that. We usually have a very high resolution of the pixels themselves and the location of those pixels. Yeah. Okay. I think the next couple of slides is more informative as an opportunity to join. So I can just go into it, and I'm excited about the project, so I'm going to talk about it. And then afterwards we have another application if we're still all awake and ready. Okay. I just want to talk a little bit about M for mining, not only because hyperspectral solutions are commercial solutions. You can buy them off the shelf, basically. But there is a lot of development happening and a lot of innovation happening. And there are a lot of active research projects and innovation projects. And we know the landscape of where hyperspectral mining can be applied, or hyperspectral can be applied in mining technically. But we have a lot of say in where it's actually been implemented, and there's a lot of potential for finding your own solutions and presenting them. I think that's unique for mining technology compared to technology that has been used in the last 50 years. So there's a lot of potential for students and people that are interested in innovation to be a part of that. It's still in the entry stage for mining. So there's a lot of things that are not defined yet, and the standards are not necessarily defined yet. And I think that's interesting, especially in a call like this for you guys. So that's why I wanted to just briefly go over M for mining, also because we're talking about UAV projects. So M for mining is a project funded by the European Union. It stands for Multiscale, Multi-Sensor Mapping and Dynamic Monitoring for Sustainable Extraction and Safe Closure in Mining Environments. I've been talking about the tailings aspect just because of that, because this project is concentrating on tailings at a big part. It's concentrating on tailings as an application, but what we're doing with HySpecs and other partners here is trying to improve the characterization of material during remining, extraction, and then also environmental impact monitoring, and developing a new hardware system for hyperspectral UAV, and implementing that with satellites that already exist. So either by upscaling or by calibrating satellite data to have a better, for the satellite data to have a higher impact, basically. Second. Yeah, so what we're doing in M4Mining, and that project just started 8 months ago. So it started January 2022 and it's gonna 2023, and it's gonna run until 2025. So we have a 3-year project ahead of us. What we're trying to do here is combine UAV, hyperspectral UAV, and hyper and also multispectral satellite for tailings monitoring. We have quite a strong consortium in the hardware and software development part, but also in the application of tailings monitoring with the University of Queensland. So what we're doing is we have a couple of projects or a couple of field and test sites where we're mapping active and inactive mining sites with our satellites and the UAV. We have the German Research Center for Geosciences as a partner, who is the scientific lead for the EnMAP satellite, which is a hyperspectral satellite that was just launched last year. And what we're also doing is looking at real-time classification from a UAV platform, which has not been done before. So we have technology and we're updating the UAV with technology to be able to get a real-time classification of whatever it is scanning. And that means real-time georeferencing and atmospheric correction. It means real-time mineral classification, real-time 3D visualization, and then hardware that enables not only scanning down as a UAV usually does, but also sideways to scan mine faces. So we don't have to bring a tripod into a mine, which is a big thing. And what we're also doing is doing that from a user-led perspective, which means we want to communicate, and we're communicating early results with on-site users, and we want to make sure that we have interactive presentations and presentation of results quite early for decision-making. We want to have a more closer dialogue with stakeholders. So we're having a mineral advisory board with people in the industry giving us feedback on this, what is essentially software and product development, as well as algorithm development. And yeah, all of that is planned on at least 4 test sites, 3 field sites alone in Australia with abandoned gold, uranium, RE tailings and active copper tailings. We have test sites in Norway with aggregate miners. We have a pyrite or an old copper pyrite mine in Cyprus and a rehabilitation site, which is state-of-the-art for rehabilitation restoration within Europe. And then we also have active carbonate hosted bauxite mines in Greece that we're looking at. And as I said, the main goal is to develop something, but also to integrate it and test it thoroughly and work with the mining industry together. And just as a last slide to list all of our partners. So especially, I mean, the universities, they already have students that they're working with, but all of the partners are very open to students approaching us, and we can figure out if there's a way to have a student project or have a thesis, a bachelor or master thesis. As I said on the first slide, if you joined later on during the presentation, please just find me on LinkedIn and reach out if you're interested in working in that area. And we can always discuss, and we're always open to help out. And one of these projects where that might be possible is M4Mining. Yeah. Okay. We have a ground-based application ahead of us, which was my PhD thesis. So I'm trying to cut it short because otherwise I usually go into very, very long dialogue about it. We have the potential to talk about core scanning as well. I'm just going to have a look at the chat. Yeah, there's some questions. Okay, 2 good questions. The first one is, I'm going to start with the one that I can categorically answer, which is Would there be any challenges in using it in the dense tropical region? Yes, very big challenges for that system, especially for UAV. So what we're usually looking for UAV applications, and you would also do that for satellite applications, is arid or sub-arid regions. If we have a bit of like dry grass and vegetation and maybe some sparse trees, all of that is fine. It is even better with a UAV because we can mask those out. They're not going to go into a mixed pixel of 20 by 20 meters. That way we are able to look through the vegetation to an extent. In a tropical region with a lot of vegetation cover, this is not a good method unless you have open pit mining and you have an open surface already. If you want to monitor a tailing that might not be covered by a dense forest yet, if you have a bauxite mining or nickel mining in general, where you have strip mining, all of these areas can be mapped for grade control or for contamination or for anything that you can think of. But in general, we need an open surface that we can look at, and vegetation is a problem. Issues of mixed pixels in places with complex scenes. So mixed pixels are in general still a topic of active research. There's a lot of different papers on it. There's a lot of different ideas on it, how to deal with mixed pixels and mixed spectra. There's a lot of training going on with it, and we're talking about neural networks, of course, and everything that goes into the AI space, because those projects usually get funded. I have a strong opinion on it, which is, I love all the research, and I think it's in very specified areas, it's very possible to unmix and to take mixed pixels into account. But it becomes very complex if you're trying to apply a model that you've trained onto a real world example. So either you need to train a lot of different models and take into account a lot of different factors, which is virtually impossible in a real life application. Or you need to accept that we might not be able to unmix everything, but we can specifically look for lithologies, where we say, okay, we're expecting a lithology, which is a mixed material. This material has this expression. If we can map that and the extent of it, maybe that gives us a good idea. It depends a lot on the actual use case and application. Yes. So I'm usually.
Can I say something about it, Doctor? Yeah. Most of the times, the problem about these small resolutions is that we have major elements and minor elements, and I think most of the times we are interested in the minor elements, but the major elements has more expression. And when you need to devote this in a big area, this big expression from the major elements will mask almost all the minor ones. Somehow, artificial intelligence, neural networks are able to overlap this situation, because instead of get information only from one feature, you can get information for 3, 4, or 5 features at the same time. And sometimes one element can be represented by 3 or 4 features, but you have one with more expression and the others with less. And when you are able to combine the information from 4 sources, sometimes you can run from the influence of the major elements and like make a ponderation of all together. So thank you just for this. Allow me to this input.
Give me 1 second, because my dog is excited about something right now.
Oh, so now no problem. Okay. Yeah, and this application of artificial intelligence in this field of study has a lot of potential exactly for this, because you can get information from different sources. Like we are used to make regressions and predictions based on a two-dimensional space, and with AI you can go on the multi-dimensional space, and this allows you to run from these problems. Sorry, thank you.
Yeah, sorry about that.
No problem.
I think another thing is that a lot of the studies where AI or machine learning or deep learning is used it's not necessarily different. They don't necessarily differentiate between spatial and the spectral domain. So for satellite data, especially if we look for land use or land cover applications, the spatial connection between different plots and areas that are labeled is actually important. So we know that if there's a car park, then the spatial pixels next to the pixel that is classified as a plot or a car park is most likely also a car park or a street. So there's a spatial correlation happening. For natural material surfaces, for exploration surfaces, for geology, we have some of these patterns, but it's very hard to train on them and to train on them reliably. So you would only have to look at the spectral domain and completely discard the spatial domain. Otherwise, we'll have models trained on minerals that might look, or if we use lab data, maybe those minerals are closely correlated in the spatial domain on the conveyor where we scanned them. But in the real life example, their spatial correlation has nothing to do with what we trained on. So that's another issue that also goes into the unmixing aspect. How do we train something with labeled data reliably, basically? Yeah. And then we have shadow effects. It depends on what we look at, but you have terrain effects and shadowing effects and sun angle effects. There's a lot of different effects. So the easiest way to not have false positives is to exclude everything from the image that you are not sure about. So you could just mask every shadow and vegetation and pixels that don't have a strong spectral absorption feature, for example. And then use a simple classifier on getting patterns instead of aiming for a mineral map that gives you every possible mineral that could be in that surface. Just as a more of an opinion piece, but yeah. Let's see. Okay, there was a question about the student project. I think in general, what I talked about is the EU-funded project, M4Mining. You can also find that. I can put that in the chat here. Oh, how do I message everyone? Here we go. So this is running and active research. So we're also looking for people to contribute to that, or for students to contribute to that. But in general, just reach out to me if you're looking for a student project or looking to work in hyperspectral. We also just have internship possibilities. So it's not necessarily bound to that project. Yeah. If there's any AI model developed in-house of NEO and for the automatic extraction of specific minerals. There isn't. We're working together with a company called Predictera, and I just put that in the chat here too. They're based in Sweden, and they're doing a software called Breeze. So we're working with Breeze, but Breeze is a chemometric software. So that's been developed for chemometric models of quality and quantification control in factory settings, basically. So we're using Breeze a lot for core scanning. They have a specific geo module that is also continuously developed. So it's not at an endpoint yet, but we have a mineral mapping capability using Breeze. Breeze has integrated the spectral angle mapper. It has integrated minimum wavelengths mapping, and it also integrated the USGS Prism Mica algorithm, which is basically a huge decision tree built by the USGS on all of the absorption features in the minerals that they have defined very clearly. The USGS Mica Prism and the minerals in that library that is being used were built for exploration. So we don't have all of the minerals that the USGS has in its spectral library. It has the minerals that are important for weathered surfaces and exploration surfaces. So we're looking at chlorides, alanites, kaolinite, different clay type minerals, possibly secondary iron, epidote, basically. Some sulfates, some carbonates as well. But it doesn't cover all of the minerals that we might be interested in. But that's the software that we're looking for. We also have but we haven't started it yet. We're looking for a smaller student project, developing a machine learning model based on published data in the sphere. But it's not, this is not like a product development. This is just a student project for testing. So we have a lot of those kind of opportunities, and we have a lot of projects that we think would be cool and that would be interesting to students as well as us. But it's not necessarily the only thing that we can do. And as for AI, again, it's not a reluctancy, but we're not actively developing into the AI space right now, because we'd rather have an explainable model instead of a black box model. And you're probably familiar with that, but a lot of companies that are offering AI are in its core just offering machine learning, which is totally fine if it works. It's just we do machine learning as well. We don't necessarily offer AI. Yeah. Yeah. And another thing with AI is labeled data. We have, and also not only labeled data, but variability within the data that we are labeling and the minerals that we're labeling. If we have an alunite from a specific, first of all, if we sample something, we would have to say with certainty, whatever validation method we're using, that this is 10% alunite, 5% kaolinite, 50% quartz. This is already impossible because most of the validation methods are not able to give you this accuracy. And they also have different strengths. As I said, if we have amorphous minerals like kaolinite or buddingtonite or dicite, those cannot really be distinguished very well using XRD. But XRD would be our main method to get mineralogy if we're trying to label mineralogy. And then if we label mineralogy, we have substitution of elements in minerals depending on when those minerals form. How do we label for that consistently? That's why I'm saying that we could try to get at the most minuscule detail of AI labeling and mineralogy, but often a more brute force method like spectral angle mapper or even minimum wavelength mapping without labels gives us patterns that we can go investigate. And they already give us patterns that are useful to follow up on and to monitor instead of getting the precise mineral. Yeah. Yeah. What did you say is the resolution of the equipment you use? That depends on the distance of the camera to the object of interest. So if we have the UAV system and we fly at 120 meter height or below 120 meter, because I think that's the usual restriction, at least in Europe and Australia and the US, we get pixels around 6 to 10 centimeters pixel size. If we work in the laboratory, we go up to the sub-millimeter, depending on if our camera is 1 meter away from the object or if it's 30 centimeters away, or if we have a microscope lens. The good thing about our cameras is that the lab cameras that we're using have adjustable lenses. So you can use a lens to get a higher resolution. You just have to change the lens. You don't have to change the system. For the Mjolnir camera that we're using, which is the UAV camera that we're developing, they now also allowed to add a 1 meter lens. They used to not, but now the systems, you can add a 1 meter lens. So it means same system that you're using from a UAV, which is without a lens, like the plain view window is sharp at, I think, 30 meters or 25. I should look that up, but you don't need to fly super high to super high to get a sharp image. You can add a 1 meter lens and put it on top of a conveyor or on a tripod, for example. So yeah, and the resolution there is then a centimeter, maybe half a centimeter. Yeah. Okay, cool. I think I would probably conclude in 9 minutes. Then we have 1.5 hours filled quite comfortably. Okay. I have more slides on my PhD project, but I'm not sure if we can just go through them briefly. I just stopped sharing my screen so I can see you guys. There we go. So this is a copper gold pyrite volcanogenic massive sulfide in the Republic of Cyprus. And I barely have any slides to present. I just wanted to give you a general overview of what is possible from a ground-based scanning. And in the Republic of Cyprus, this is where the Cyprus type volcanogenic massive sulfide was defined. So it's quite a nice area to work in with research, but there's not a lot of active mining going on right now. When we were there in 2018, Skouritissa mine was the largest operating mine here. And Apliki, which was my main area of interest, was discontinued since the 70s, I think. Now it's the other way around. Now we have Skouritissa is closed or was closed in 2019, end of 2019. Now they're thinking about reopening Apliki. The whole area in general is very interesting because there's a lot of mining activity that happened there, even in the antique times. So you see a lot of waste and smaller waste disposal sites, as well as open pit mines that were active in the 1970s, both for pyrite, but also chalcopyrite. And we have some carbonatite limestone mines there as well. But in Apliki itself or in Skouritissa, so both of these belong to the same type of mineralization. We expect pyrite, chalcopyrite, and sphalerite, with galena and secondary copper-bearing minerals as the mineralization of interest. And then we see the typical alteration in a VMS deposit, similar to what I showed you in cuprite. So we expect silica alteration, chlorite, disseminated pyrite, argillic, phyllic, propylitic, potassic alteration zones. Everything that you would expect from a hydrothermal alteration pattern. And as I said, we are not able to map pyrite or chalcopyrite or sphalerite or galena directly, at least not with ground-based, maybe in the lab, but not in the application here. So what we're looking for in mapping hyperspectrally is mixtures of jarosite, goethite, hematite, and different clay minerals that characterize the different alteration zones. And what we did here, so this is Apliki mine. Again, it was discontinued in 1970 something. So we have a larger open cut, and then we have areas that are just surrounding host rock covered by vegetation. So what we're interested in is this open cut here. And just to show you the system again, it becomes a bit clearer, at least a little bit. We have a tripod and we have our camera mounted to the tripod, and it collects the data in a rotational manner. As I said, we just collect one line of pixels. So we need to either move the sample or move the camera. And in this case, we're moving the camera in a rotational manner, collecting line by line into one image. And that's what you are seeing here. There we go. So this is the position of where our camera or sensor is, and then we're collecting this area just as an exploratory data set. So we're covering the full open cut, and we're covering all of the alteration zones that we can see, because we know that the stockwork is going in that direction in this case. And what we're interested in would be specific mineralization, but because that is really, really hard to get, as we just discussed before, we're here looking more for clusters, and the clusters are defined by the chemistry of samples that we took, by the spectra, and basically by the chemistry and the spectra and the mineralogy. So we had the samples analyzed in the lab, we looked at the spectra expression, we looked at the chemistry, and in the end we came by 6 different clusters that represent the surrounding host rock, which is the pillow lava, weathered sulfide ore, silicified areas, more massive mineralization, smectitic, and then chloritic stockwork. And I just wanted to show you the results of 2 different analysis types here, basically, just to give you an idea of what the result is and how the interpretation would go. So the top image here is a knowledge-based approach, where we know that we're interested in a very specific wavelength region. So this is a simple bend ratio of around 2,290 and 2,350 nanometers, where we know that we are looking for the expression of mica versus chloride. And you can see how that index, the MGOH index in that case, how it increases towards the center of our open cut, at least a little bit in intensity. And yeah, we just want to make sure this would be one way of figuring out, okay, where's an area of mineralization, or at least where's a pattern that we want to investigate further. And the pattern here would be, well, we're not expecting a lot to happen in the pillow lava, where we can see even in the open cut, there's a trend towards the center of this open cut. And then the comparison-based analysis, similar to what I said before, we're comparing an unknown spectra with a known spectra from a spectral library. The spectral library in this case was built in the lab on samples from the site. So we don't have the classification as a mineral, but we have the classification as the cluster or lithology. And what you can see here is that the weathered sulfide ore also seems to follow a trend in the center. But then what matches with the MGOH index is the chloritic stockwork. So you can see that the chloritic stockwork, though it also maps towards the outer edges here, is more centralized into the center of this open cut. And what we can see, what is not on this extra hyperspectral image, is that we have a Gaussian on top of that. So if we had an exploration project here, and this was not an open cut, we would still have the surface expression of Gaussian top, basically, of that stockwork. But you can also see that the areas around it are quite well classified as pillow lava. So even if we can't label anything, we know that there's a difference between the patterns that we can see and the differentiation of patterns that we can see in the open cut versus the unmineralized zone. And we did something different for Scaritissa mine itself. And there we went into 3 hills. So that's the tiny little arrow there, a small pit, especially small scale compared to other copper extraction sites, open cuts. And because Cyprus is generally a little bit more small scale, what we're interested here is to just classify samples based on the copper content. So it was a very simple library with samples classified and having copper content below 0.27% or around 0.27, between 0.1 and 0.27, and then below that with a high clay content. And the actual mineralization here is around, like the grade is around 0.27 or was around 0.27% of copper in that pit. And what we just wanted to see is how a pattern emerges on this open pit. We know that there's a fault running east to west through the pit. I tried to show that here, but this is actually cutting into the open pit. So there's a fault running here. We know that there's lower copper grades north of that fault and higher copper grades south of the fault. That's why the pit was developed towards the south of that fault. And we can see that quite well reflected in the actual mapping, where everything red is lower copper grades, everything pink is higher copper grades. And then we can see the fault line quite well because we see more weathering happening here in terms of clay showing up. So this is by no means the perfect analysis or something that we would use to influence deposit modeling at that point, but it's a good feasibility of showing that the patterns that the hyperspectral data shows are consistent with what the deposit modeling and the geological model and the general knowledge about the grade occurrence in this pit showed. And then you can refine it from there. Yeah, and I think I would cut it here. Are there more questions coming up? I'll just stop sharing for a second so I can see you guys. Okay. I will just put my work email in here instead. Please make sure that you remind me where you heard of me or when we talked, so I know that this is the TechNG. Otherwise, it's going to be very hard for me to link you to a specific event.
Thanks.
Yeah. Yeah. So that's the question for the LinkedIn. If you are on LinkedIn, just feel free to reach out and connect. Then the messaging, I didn't know that the messaging feature is deactivated. I have to check that. Yeah.
Yeah, usually I think when you have something private, people can follow you but cannot ask for connection. But if they go to the three dots on the right, I think they can ask to connect anyway.
Yeah. I'm pretty sure that that's not disabled, but I don't have a LinkedIn premium membership anymore. That might change my open profile. I should investigate that. Yeah.
The same question from before.
Yeah, it can't be deployed for groundwater survey. I'm sorry. Just a surface measurement. Unless something at the surface is an indicator for groundwater. So if you have vegetation, an example is also, for example, at the front of a tailing, there's different, if vegetation crops up at the edge of a tailing, there's probably water flow coming from the tailing that we want to avoid. Like you have different proxies that you can use, and I'm sure there's proxies for groundwater as well. Yeah, but I have very little experience with vegetation remote sensing. There's a lot of, apart from mining, there's a lot of different applications using hyperspectral, not only land cover and land use, they're also using it for species detection and reforestation. It's been used for archaeological applications, for agriculture, for smart mining, like this, lots of different ones. And for surface measurements for groundwater, I know that there's been studies in determining determining water content or even quantitative mapping of water bodies. I know for mining water bodies, we usually have a higher suspended load. In that case, you can map something. If we're talking about very deep or very fast flowing structures, it is probably more complicated or impossible. But again, I don't know. I can't say it's impossible.
Okay. So if we don't have any more questions, I could talk a little bit. Today we went from the specifications of spectroscopy. We went through equipments and sensors and even technical information. We went through AI and then that amazing case studies that are very demonstrative of what is the potential application of these methods. And I need to thank you a lot for accepting to be with us. We are a small organization, but we are trying to make impact in these students and these recent graduated that want to follow their path and find the best way to achieve dreams and professional goals and everything. I think it's very important to have people like you that spend time to share your knowledge. Okay.
Thank you so much for the invite. No, thanks for the invite. I appreciate it.
Yeah.
Very, very easy to say yes to something like that.
Thank you. I would like to make just 3 final remarks about what we talk today. We talk about near infrared and shortwave infrared, but we also have other type of infrared, like you talk, like middle wave and far infrared, and there we are talking about an exponential high price about the equipment and the sensors, and that's why these sensors are the most used in mining nowadays. And the others, I think they use more for spatial satellites that go to investigate all the planets and everything, because there you have investments that are able to do in these fields. We talked a little bit about AI, probably not in the plan for the meeting and the presentation, but AI is the topic of the moment. So for sure it will appear. But we should concern about the computer cost of this type of algorithms, because sometimes with a simple regression or even a multilinear regression, you can do the same effect of an AI, and you will have a really smaller computer cost, and it's very important, because the equipment that we are talking about, like drones, they are not heavy and they are small for this purpose. And when you go on a higher computer cost, you need to implement more robust, more heavy equipment, and it's something to concern about. And the last topic is really the other applications, but you already talked about this. It's not only mining, you can use in many things, even traffic control. They use sensors, they use satellites and this hyperspectral imaging to find movement, to motion. So we have a lot of applications to do in this field. So thank you very much again. And
thank you. I just put a link into the chat for other application notes, because we have colleagues at HySpecs that look at smart mining and that look at industry applications. It's just not me, but there are some examples, and yeah, maybe they give you a better idea of other application cases as well.
Okay, thank you.
Yeah.
Joshua, do you want to say something, or you are muted?
Yes, actually, I don't really have much to say than to appreciate guest speaker for today, Dr. Cotin. I don't know if my pronunciation is right.
Yeah, good.
Yeah, so thank you very much for creating time out of your busy schedule to be with us today. Like Sanchez said, we need great people like you to be of influence to young people, not just in Africa, because when you see most of our trainings, we intend it to be for Africans, but at the end, we have people from different parts of the world participating in the program. So it shows to a larger extent that we are really doing great job. And one of the great work we were doing was noticed that was early this year at an institute in the Netherlands. Then we did something with a professor on water studies. So I hope and I believe in the nearest future, this relationship we have established will be. And in the case of next time when we invite you, I know you would surely honor our invitation too. So Sanchez, I just want to thank you too for, you've really done a great job in the coordination of the event. And also Jumoke, who is also an environmental geoscientist from Nigeria, who is supporting underground Sanchez in today's webinar. So Sanchez, I want to say a big thank you. And I can also see Rio Frutuoso, whom we'll be having tomorrow. So it shows a lot of, this really talks a lot about his personality, because I see he connected from the beginning and then till now he's still with us. Thank you very much, sir. So Sanchez, that's all I have to say. I look forward to an exciting moment. For me, I'm not from the mining sector, but I'm from the environmental sector. And I could see when a guest speaker was saying something about the application of these hyperspectral imageries in environmental management. It's really a powerful tool. In one of the projects I joined, it was basically on agriculture, and we used these in mapping the amount of carbon sequestered by the soil, by agricultural soils, and the study was specifically in Europe, in Italy, and again for fire management, ecosystem management, etc. So it's something so huge, and I want to assure participants that are here today that we really learned a lot, and we would make the video available on our YouTube channel. And as well, you can always see the recording, the live recording. Again, you can rewatch on the Facebook. So if you want to connect with us, Sanchez has done a great job sharing the link to our WhatsApp platform on the chat, and as well, the link to our website. It is itagng.org. So Sanchez, over to you. Thank you.
So thank you again, and I hope to see you all in our tomorrow's event with Rui Frutuoso, that is with us today in the presentation. So if we don't have anything to say, Doctor, we could close the session.
No, all good. If you have more follow-up questions on providing links, just let me know, and maybe we can have an email with everyone who's interested in the information from today. so we don't repeat that over 20 emails.
Okay.
But I'm happy to just follow up on that. Just let me know.
Okay. So thank you. Thank you very much.
Thank you so much, guys. Have a great evening.
Bye.
Bye.